How many ways can a world die? If planets are born, do they all have to die? And if they do, how many different endings does the universe actually offer them? We usually think of a planet as a stable backdrop, a quiet stage where life, if it is lucky, plays out its brief drama. But while we talk about the birth of worlds from swirling disks of gas and dust, we rarely ask a more unsettling question. How does a planet's story end? Does it freeze? Boil? Shatter? Simply fade away into the dark? It should be noted that, from the perspective of astrophysics, planets are not immortal. They are trapped inside a larger system of forces that never stop changing. Their parent star brightens, swells, or explodes. Orbits shift. Atmospheres leak. Deep interiors cool and solidify. This means that a planet like Earth does not have just one possible death, it has several. On our own world, we can already map out a few. As the sun slowly brightens, Earth's oceans could be driven into a slow, relentless boil, turning our blue planet into something more like a humid Venus. Far later, when the sun becomes a red giant, its outer layers may expand so far that Earth is engulfed outright, swallowed by the very star that made it habitable. And even if we somehow escape those fates, internal cooling and the loss of a protective magnetic field could quietly strip away our atmosphere over immense timescales. In the hunt for alien life, we have accidentally stumbled onto a catalog of planetary deaths. Astronomers have found disintegrating planets skimming their stars in orbits lasting less than a day, their rocky surfaces literally vaporized, trailing comet-like tails of dust. We have detected lonely rogue planets, flung out of their original systems, drifting through interstellar space where starlight never rises, their surfaces locked in eternal, airless night. We have also seen scorched hot Jupiters, gas giants parked so close to their stars that their atmospheres are blasted away by radiation, layer by layer. Some worlds are stripped down to dense, exposed cores. Others may spiral inward until they are torn apart by tides, feeding their stars in a final, incandescent plunge. Optimistically speaking, these are not just curiosities, they are previews. So, let's begin with a bold promise. In this video, we are going to build a complete menu of planetary death, from the first light of a newborn star to the fading embers of a dying universe. We will follow every major way a world can end, and ask where Earth fits on that menu. So it's time to find out the truth. Some planetary deaths unfold in seconds, erased by supernova shockwaves or tidal shredding near black holes. Others outlast entire galaxies, stretching toward the heat death of the cosmos. And one of those endings, in some form, is almost certainly waiting for us. Why planetary death matters long before it happens. If every planet must die, why spend so much effort learning the details of those deaths? There is a simple reason. In the hunt for alien life, the way a world ends is often the clearest clue to how it lived. We usually imagine planetary death as pure science fiction doom, a distant explosion at the end of the story. But while that makes for great movies, astronomers treat these endings as scientific tools. Each dead or dying planet is a fossil in motion, letting us read the life story of a world, how its star behaved, how its atmosphere evolved, and how long it stayed habitable. This means that when we study how other planets are destroyed, we are quietly learning how long Earth can keep supporting complex life. So, let's begin with our own star. Sun-like stars slowly brighten over billions of years. Even long before the sun becomes a red giant and threatens to engulf the inner planets, that brightening will push Earth out of the comfortable Goldilocks zone. At some point, oceans start to evaporate, the atmosphere fills with water vapor, and a runaway greenhouse takes over. The practical question is not just will the sun swallow Earth, but when does Earth stop being truly Earth-like, and what warning signs would we see first? Subtle shifts in atmospheric composition, changing cloud patterns, and the loss of our protective ozone layer are all on the list. It should be noted that we cannot simply sit back and watch a single planet run this entire course in real time. Human lifetimes are far too short, so astronomers cheat in a very clever way. They stitch together thousands of snapshots from different systems at different ages. A close-in world stripped to a rocky core here, a bloated red giant star swallowing its inner planets there, a frozen rogue planet drifting between stars somewhere else. From this cosmic collage, a timeline of planetary life and death slowly emerges. Each death mechanism leaves its own fingerprints. Stellar violence scours atmospheres or erases planets entirely. Orbital chaos flings worlds into their stars or out into interstellar space. Atmospheric escape carves away hydrogen or water, as we see in evaporating ultra-short period planets with comet-like tails. Internal death shuts down magnetic fields and tectonic recycling, as Mars likely did. Optimistically speaking, our telescopes are now good enough to read these signatures. Kepler and TESS have revealed stripped rocky cores. JWEST measures the heat and chemistry of scorched, boiling, or frozen worlds. So it's time to find out the truth. By comparing those distant fingerprints to Earth, we can start to place ourselves on the menu of possible endings. And there is a quiet twist. One particular path to planetary death has already begun here, right now, in our own atmosphere and oceans. But before we can name it, we need one more crucial piece of the puzzle. From TRAPPIST-1 to the deaths of worlds, that missing piece is this: we have already watched other planets die. Not in science fiction, but in hard telescope data. Think back to TRAPPIST-1. In the hunt for alien life, we first met it as a hopeful place. 7 Earth-like worlds, packed tightly around a small red dwarf. Some in the Goldilocks zone, some maybe even habitable. But while we looked there for oceans and atmospheres, TRAPPIST-1 was also showing us something darker. It was quietly demonstrating how easy it is for a planet to lose everything. Those inner TRAPPIST-1 planets are squeezed so close to their star that a year lasts only a few days. They are tidally locked, with one face in endless day and the other in permanent night. The red dwarf flares, bathes them in high-energy radiation, and its stellar wind claws at any atmosphere they try to hold. This means we are seeing, in fast-forward, processes that in calmer systems like ours might unfold over billions of years. It should be noted that TRAPPIST-1 is actually a relatively quiet red dwarf. Yet J-West has already shown us worlds there that are airless, scorched, or probably drowned under superheated oceans. Now scale that up to more violent stars, closer orbits, denser clusters of planets. Suddenly TRAPPIST-1 stops looking like an oddity and starts looking like a laboratory for death. Why is that so powerful? Because compact systems compress time. Tidal forces are stronger, orbital resonances are tighter, flares hit more often and with more intensity. Planets migrate, atmospheres evaporate, orbits decay, and sometimes worlds are even torn apart, leaving behind rings of dust. We can watch, almost in real time, the same basic physics that will one day decide the fate of Earth. So, let's begin to reframe the question. A planet does not have one single cause of death. It has a chain of vulnerabilities. What kills a world depends on its star brightening or exploding, on its orbit shifting, on whether its atmosphere can shield and cool it, and on whether its interior can power a magnetic field and plate tectonics. Change any one of these, and you change the ending. To make sense of this, we need a map. So it's time to find out the truth in a structured way. We will start at the center, how stars kill planets through slow heating, red giant engulfment, and sudden outbursts. Then, we will move outward to gravity itself, to the orbital rearrangements that fling planets into their stars or out into interstellar space. After that, we will peel back the layers of air and rock. We will see how atmospheres are stripped or suffocated, and how interiors freeze, crack, and finally go geologically silent. Finally, we will push far into the deep future of the universe, where even surviving planets face truly exotic fates near black holes, or in a cosmos that is running out of usable energy. And then, we will turn all of that back on ourselves. Given everything we have now seen in other systems, which death is actually most likely for Earth? Which nightmare endings can we rule out? And which ones are already quietly starting, right now, under our feet and above our heads? The star's executioner, how suns kill their planets. So, if we want to know how a planet dies, we have to start with a very uncomfortable truth. The executioner is usually the same star that once made that planet habitable. A star is not a static lamp in the sky, it is a fusion engine that slowly changes its fuel mix, its brightness, its temper. This means the very light that feeds a world's ecosystems will, over time, shift into a weapon. For a sun-like star, the power output creeps up by roughly 10% every billion years. That sounds gentle, almost harmless. But while that rise is slow, the consequences are not. As the star brightens, the inner edge of the Goldilocks zone moves outward, oceans start to evaporate, the atmosphere fills with water vapor, and a runaway greenhouse can lock in. We think this is how Venus became a cautionary tale. In the hunt for alien life, those subtle changes in starlight can quietly turn an Earth-like planet into a sterilized rock over just a few 100 million years. No explosions, just a slow boil. But long-term brightening is only the opening act. When a sun-like star runs out of easy hydrogen in its core, it swells into a red giant. Its radius can grow hundreds of times, sometimes reaching or even exceeding the current orbit of its inner planets. We have already seen distant red giants with dusty rings that may be the shredded remains of former worlds. It should be noted that in this phase, tidal forces and drag in the swollen stellar atmosphere can pull planets inward, spiraling them to their deaths. More massive stars are far less patient. They live fast, burn furiously, and then end as supernovae. In a single event lasting seconds to minutes, shockwaves and intense radiation can strip atmospheres, melt surfaces, and disrupt orbits across an entire system. Even a planet that survives physically may be left airless and frozen, a corpse drifting through its ruined neighborhood. And in the most extreme cases, a collapsing massive star can launch narrow gamma-ray bursts, beams so intense they could sterilize worlds light years away if they happen to be in the line of fire. At the other end of the scale, small red dwarf stars can live for trillions of years. Optimistically speaking, that sounds perfect for life. But while their fuel lasts, their magnetic tantrums do too. Flares and particle storms can batter clothes and planets on timescales of minutes to hours, slowly eroding atmospheres that took eons to build. So it's time to find out the truth about our own sun. It will never explode as a supernova, but its steady brightening and eventual red giant phase are already setting a hard deadline for Earth, long before the universe itself goes dark. Slow burn. When your star quietly boils you alive, so if our sun is already on a countdown, what does that actually feel like from the surface of a planet? Not as a single cataclysmic blast, but as a very slow fever. Main sequence stars like the sun are often described as stable, but while they look calm, their cores are changing. As hydrogen fuses into helium, the dense helium ash builds up in the center. The core contracts, heats up, and the star burns its remaining hydrogen faster. This means its total energy output rises over time, even though to us it still looks like the same familiar yellow disk in the sky. For the sun, the increase is roughly 10% every billion years. That sounds small. But for a planet balanced delicately in a habitable Goldilocks zone, it is not small at all. The zone where liquid water can exist is not fixed. As the star brightens, this habitable ring drifts outward. A world that once sat comfortably in the middle can find itself pushed toward the inner edge, then beyond it, without its orbit changing by a single kilometer. So, let's begin with the only detailed case we truly understand, Earth. Current climate and stellar evolution models suggest that in about 1 to 2 billion years, rising solar luminosity will push us into a moist greenhouse state. Oceans will evaporate faster than they can condense. More water vapor, a powerful greenhouse gas, will trap even more heat. This feedback loop slowly transforms the atmosphere into a steam blanket. It should be noted that this is not science fiction. The physics is the same greenhouse effect we worry about today, just driven by the sun instead of our emissions. As the upper atmosphere fills with water, ultraviolet light from the star splits those molecules. Hydrogen, the lightest element, then escapes to space. Over hundreds of millions of years, Earth's oceans are bled away, molecule by molecule. In the hunt for alien life, this moving target is crucial. A planet can be Earth-like for a few billion years, then quietly slide into a runaway greenhouse that sterilizes the surface long before the star becomes a red giant. We may already be seeing the end states of this process. Close in exoplanets that JWST and earlier missions have found, hot rocky worlds with bare scorched surfaces could be the stripped cores of former mini-Neptunes, their thick hydrogen and helium atmospheres boiled off by relentless starlight. Optimistically speaking, some systems might enjoy longer stable windows than ours. Cooler stars brighten more slowly, but while that buys time, it does not grant immortality. Even the calmest star eventually turns up the heat. And remember, this is the gentle version of stellar murder. So it's time to find out the truth about what happens when the star stops simmering its planets and starts reaching out, physically, to swallow them whole. Red giants and planetary engulfment, the ultimate close call. So, what actually happens when a star stops simmering and starts to swell? There are few moments in a planet's life more dramatic than the day its sun turns into a red giant. When a sun-like star runs out of hydrogen in its core, fusion does not simply turn off, it moves outward. The dead core contracts and heats up, while a shell of hydrogen around it ignites. This shell burning dumps energy into the outer layers, and the result is extreme. The star's atmosphere expands to hundreds of times its original size, and its luminosity can jump by more than 1,000. It should be noted that this is still the same star, the same mass, but wrapped in a bloated, cooler, red envelope. Simulations of stars like our sun show just how far that envelope can reach. In the models, the red giant sun could swell until its radius is roughly the size of Earth's current orbit, maybe a bit less, maybe a bit more. This means the inner solar system stops being a comfortable Goldilocks zone and becomes the inside of a furnace. Mercury is swallowed early, Venus follows soon after. The details depend on the exact mass loss and internal physics, but the trend is clear. The inner planets are in deep trouble. But while we might imagine a hard boundary between inside the star and outside, reality is messier. A red giant's atmosphere is extremely extended and diffuse. Planets that start just beyond the visible surface can still plow through that gas every time they orbit. Tidal interactions stretch both the star and the planet, and drag from the stellar atmosphere saps orbital energy. Orbit after orbit, the planet spirals inward. Even a world that technically begins outside the swollen star can be slowed, pulled down, and eventually vaporized. So where does that leave Earth? Current best estimates are ruthless. Mercury and Venus are almost certainly doomed to complete engulfment. Earth, though, sits right on the knife edge. Some calculations suggest that as the Sun loses mass, Earth's orbit will expand just enough to escape direct swallowing. Others, using slightly different data and drag models, find that the extended solar atmosphere still reaches us, pulling our orbit inward until the crust and mantle are stripped away. Optimistically speaking, the survivor version of Earth is not a blue marble. It is a scorched, atmosphere-free cinder, its oceans boiled off long before, its surface glowing dull red under a swollen sky. All of this might sound like distant speculation, so let's begin a quick jump to real time. In 2023, astronomers actually watched a star in our galaxy engulf a planet-sized object, catching the flash as the world plunged into the stellar envelope. In the hunt for alien life, we usually look for gentle, stable systems. Here, we were watching the opposite, a live planetary death. And our own far future suddenly looked a lot less abstract. Supernovas, gamma ray bursts, and instant sterilization. But what if that live planetary death we saw in 2023 was actually one of the gentler endings? Because some stars do not slowly swallow their planets, they end by detonating, and when they do, entire systems can be erased in an instant. When a very massive star runs out of fuel in its core, gravity finally wins. The core collapses in a fraction of a second, rebounds, and the outer layers are blasted into space as a core collapse supernova. So, let's begin with the scale. For a few days, one dying star can outshine an entire galaxy. This means a flood of high-energy radiation, neutrinos, and a shockwave racing outward at thousands of kilometers per second. What does that do to any nearby planet? At close range, it is not just bad for life, it is bad for rock. Within a few light years, the so-called kill radius, planets can have their atmospheres stripped, their surfaces flash-heated and partially melted, and their orbits destabilized by the sudden loss of stellar mass. Anything remotely Earth-like inside that zone is not just rendered uninhabitable, it is sterilized. Farther out, the destruction is quieter, but still deadly. High-energy photons can shred the ozone layer of a planet, leaving the surface naked under harsh ultraviolet from its own star. In the hunt for alien life, that matters, because you might look at a calm, sun-like star and a planet in the Goldilocks zone and think it is safe, while the real killer went off light years away, thousands of years earlier. It should be noted that supernovas are actually the broad version of this threat. There is an even more focused weapon, gamma ray bursts. In some collapsing stars, or in merging neutron stars, the energy is funneled into narrow, relativistic jets. If one of those jets happens to be aimed at a planet, the beam can dump more energy into its atmosphere in seconds than its star provides in years. How far does that reach? Models suggest that a powerful gamma ray burst inside our galaxy could damage atmospheres across tens of thousands of light years along its path. Optimistically speaking, the beam is narrow, so the odds for any one world are low. But while the probability is small, the consequence is enormous. So, are we at risk? So it's time to find out the truth about our own star. The Sun is not massive enough to explode as a core collapse supernova, and it is not the kind of rapidly spinning giant that launches classic gamma ray bursts. In that sense, we are lucky. However, many planets do not live around quiet, middle-aged stars and sparse suburbs. They form in dense, chaotic stellar nurseries where massive stars are common and close. In young galaxies, packed with fresh gas and frequent star formation, nearby supernovas and gamma ray bursts might be routine planetary death sentences. If some stars can wipe out worlds in a heartbeat, gravity offers a slower, more patient kind of doom. Orbits that look perfectly stable today can, over millions of years, twist into lethal paths. How does a seemingly safe orbit turn into a guaranteed death spiral for a planet? Orbital Russian roulette. Gravity's long game gravity, it turns out, does not share our sense of long-term safety. What looks calm now can, over millions or billions of years, become a slow-motion execution for an entire planetary system. We often picture orbits as perfect clockwork, planets tracing the same paths forever. But while that image is comforting, it is also wrong. Every planet in a system tugs on every other one. Every passing star adds a tiny nudge. And over deep time, those small gravitational whispers can add up. This means a world that starts in a safe, almost Earth-like orbit can be pushed into a path that is anything but habitable. So, let's begin with one of gravity's favorite tricks, orbital resonances. When two planets orbit their star in simple ratios, like 2 laps for every one, their repeated tugs can lock together. Sometimes this is stabilizing, as in the case of some moons in our own solar system, but in a more crowded system, resonances can pump up orbital eccentricity, stretching a planet's orbit into a long ellipse. Now, instead of a gentle circular cruise through the Goldilocks zone, the planet dives close to the star, then slingshots far out, boiling and freezing in turn. If that sounds chaotic, planet-planet scattering is even more dramatic. Imagine several giant planets forming too close together. Over time, their mutual gravity can kick one into a wildly inclined orbit, slam two into a catastrophic collision, or eject a world entirely from the system. The result is a rogue planet, drifting through the universe with no star at all, its atmosphere slowly freezing in endless night. It should be noted that distant companions can be troublemakers as well. A far-off star or massive outer planet can trigger what astronomers call kozai, lead-off oscillations, slowly tilting and stretching an inner planet's orbit. For ages, nothing seems to happen. Then, suddenly in astronomical terms, the orbit becomes so elongated that the planet skims dangerously close to its star on each pass. Tidal forces heat it, drag on it, and begin to shrink the orbit further. Over time, those tides can pull a planet inward, turning it into an ultra-short period world that orbits in less than a day, or even a hot Jupiter parked right next to its star. In the hunt for alien life, many of the strangest exoplanets we see today are probably the survivors of ancient gravitational chaos. The last stable configurations after earlier worlds were thrown out or destroyed. So it's time to find out the truth. Gravity's long game does not always end with survival. Astronomers have now caught a planet in the act of spiraling into its star, its death written in real-time data. What does a doomed world look like in its final orbits, and how close is that fate to our own future? Spiraling in, planets that fall into their star's A-planet can die without a single explosion. It can simply lose the delicate tug-of-war that keeps it in orbit. When a world circles very close to its star, the gravity on its near side is stronger than on its far side. Both bodies are stretched into slightly squashed, egg-like shapes. These are tides, and just like the moon raises tides on Earth, close-in planets raise tides on their stars. But while ocean tides just slosh water around, these cosmic tides move entire layers of stellar plasma. That motion steals and trades angular momentum, and over time, it quietly rewrites the orbit. In some configurations, this means the planet is slowly pushed outward, like our moon drifting away from Earth. But while that sounds comforting, other configurations are far more dangerous. If the star's rotation lags behind the planet's orbit, tidal forces act like a brake on the planet, draining its orbital energy. The orbit shrinks, the year gets shorter, and the world begins a long, spiraling fall. This means a planet can be doomed millions of years before it ever touches the stellar surface. Astronomers have now caught a textbook case. WASP-12b is a hot Jupiter, a gas giant so close to its star that it completes an orbit in just over a day. Its gravity and the star's gravity pull each other into distorted, egg-like shapes, and the tidal heating is intense. Careful timing of its transits has revealed that its orbital period is changing. The planet is actually speeding up as it spirals inward. It should be noted that this is not theory alone. We are watching the clock tick down on a real world that will likely be torn apart or engulfed in a few million years. In the hunt for alien life, worlds like WASP-12b's are terrible candidates, but they are perfect laboratories for planetary death. Many hot Jupiters show similar signs of tidal stress, their atmospheres puffed up and streaming away under the star's glare. Some may not even survive long enough for complex chemistry to stabilize. And it is not just giants. Ultra-short period rocky planets whip around their stars in less than a day, some in just a few hours. Their dayside temperatures can exceed 2,000 degrees Celsius, hot enough to vaporize rock. Telescopes have detected these worlds shedding material, forming comet-like tails of silicate vapor. Imagine an Earth-like planet so close that mountains literally evaporate into space. Optimistically speaking, that is about as uninhabitable as a surface can get. But what if a planet does not fall in at all? What if, instead of spiraling toward the fire, it is kicked completely out of its system and into eternal night? So, let's begin to explore the opposite extreme, planets that die by being exiled to the dark between the stars. Rogue worlds. When planets are thrown into the dark, being thrown into a star is one thing, but what if the universe chooses a slower punishment, exile? In a planetary system with multiple worlds, gravity is not a calm, orderly dance. It is a constant negotiation. Every close pass, every resonance, every tiny tug trades energy between planets. Most of the time, those trades average out, but occasionally, especially especially in crowded young systems. The orbits cross. Two giant planets swing past each other, and one of them steals just enough energy to leap outward. The other is kicked inward or flung away entirely. This process is called planet scattering, and it is one of the most efficient ways to kill a world without breaking it apart. If a planet gains enough speed during these encounters, its path stretches from a neat ellipse into a long, open curve. This means the planet is no longer bound to its star at all. It simply leaves. The same thing can happen when a passing star brushes by a system and yanks on the outer planets, like a thief grabbing the weakest link in a chain. So, let's begin to picture the result. A world, perhaps once Earth-like, suddenly finds that its parent star is shrinking in the sky with every orbit. One last swing, one last gravitational kick, and the star never comes back into view. The planet has become a rogue world, a starless wanderer drifting through the galaxy, not tied to any system, almost impossible to see. How do we even know such worlds exist if they are so dark? Here, the universe gives us a rare observational trick. When a rogue planet passes in front of a distant background star, its gravity briefly magnifies that star's light. We see a tiny, temporary brightening called a microlensing event. It should be noted that this effect depends only on mass, not on light, so even a frozen, airless rock can reveal itself. Infrared surveys have also turned up lonely, still warm giants glowing faintly in the dark. But what is life like on such a world, if life ever arose there at all? Without a nearby star, the surface temperature plunges toward the coldest possible limit, just a few degrees above absolute zero. Any atmosphere not locked in by gravity and chemistry will condense and fall as exotic frost. The oceans freeze from the top down and keep going. Yet the story is not entirely over. Deep inside, radioactive elements and leftover formation heat can keep a planet's interior warm for billions of years. If it began with a thick atmosphere of hydrogen or other greenhouse gases, that blanket could trap internal heat. Optimistically speaking, there might be subsurface oceans, dark but liquid, sealed beneath kilometers of ice. In the hunt for alien life, even these orphaned worlds have been imagined as potential refuges. But as the internal heat fades, the ice thickens, the last cracks seal, and the planet's geology falls silent. No supernova, no tidal shredding, just a slow, lonely freezing to death on cosmic timescales. So it's time to find out the truth about a more delicate kind of doom. Because before a planet is exiled, boiled, or swallowed, something else can be stripped away first: the thin, fragile atmosphere that makes a world habitable at all. Atmospheric armor, the first line of planetary defense. So, if a silent, frozen core is the end of a planet's story, what keeps a world alive long before that happens? In the hunt for alien life, there's one feature we keep coming back to, again and again. An atmosphere is not just a layer of gas, it is armor and thermostat at the same time. It should be noted that without air above our heads, Earth would be a brutally simple place, searing hot on the dayside, unimaginably cold at night, blasted by unfiltered radiation from the star. Instead, our atmosphere scatters harmful ultraviolet light, absorbs some of the most dangerous high-energy photons, and lets just enough through to warm the surface. But while shielding is crucial, climate control is just as important. Moving air and clouds redistribute heat from equator to poles and from day to night. This means liquid water can exist over large areas, not just in a thin ring of twilight. On a tidally locked world in a tight orbit, that heat transport could be the difference between a habitable twilight band and a planet with one frozen hemisphere and one vaporized hemisphere. So, let's begin to strip that armor away and see what kills it. Close to a star, gas molecules in the upper atmosphere move faster as they absorb energy. If they move fast enough, they simply escape, one by one. This thermal escape slowly bleeds a planet, especially if gravity is weak. At the same time, charged particles from the stellar wind slam into the upper atmosphere. Without a strong magnetic field, those particles can sputter atoms into space, carving out whole layers over billions of years. Higher energy radiation adds another attack. X-rays and extreme ultraviolet light break molecules apart and heat the upper atmosphere until it balloons outward. That puffed up gas is easy for the star to grab, a process we call photoevaporation. Around active red dwarf stars, this can strip a young planet's hydrogen and helium envelope before it ever has a chance to become Earth-like. And then, there are the sudden deaths. A giant impact, like the ones common in young systems, can blast an atmosphere off in hours. One unlucky collision at the wrong angle, and most of the air, and even oceans, can be launched into space. We can actually see the scars of this in the exoplanet data. When we plot planet size against orbit, there is a strange radius valley between rocky super-Earths and puffier mini-Neptunes. So it's time to find out the truth. That gap is best explained if many of those mini Neptunes had their gaseous envelopes stripped away, leaving behind bare, dense cores. Optimistically speaking, some of those cores might still hold thin, secondary atmospheres, but once too much air is gone, a world can end up airless and frozen like our moon, or bare and scorched like Mercury, effectively dead to surface life even while its star still shines. And in at least one case, we have watched something even more extreme. A rocky planet so close to its star that not only its atmosphere, but its very crust, seems to be evaporating in real time. Boiled from the outside in, disintegrating and evaporating planets, we usually think of planets as solid, permanent things. But what happens when a world gets so close to its star that it starts to behave more like steam than stone? One of the most dramatic examples we have is Kepler 1520b. Its orbit is so tight that a year lasts just a few hours. When astronomers watched it cross in front of its star, the transit signal was strangely irregular, almost frayed at the edges. This means the planet is not a clean, sharp disk. It is trailing a dusty cloud of its own material, like a comet made of shredded rock. What could do that? Intense stellar irradiation cooks the dayside to well over 1,000 degrees. At those temperatures, rock and metal do not stay solid. They vaporize, forming an atmosphere of rock vapor that flows away from the planet. As this vapor moves into cooler regions of the orbit, it condenses into tiny mineral grains. Those grains form a tail that curves behind the planet, sculpted by radiation pressure from the star. So, let's begin to see this for what it really is. We are watching a planet lose mass in real time. Each transit, a little more of its crust is missing. Over millions of years, the original world may shrink from something Earth-like to a much smaller, dense core, and in extreme cases, be whittled down until almost nothing remains. It should be noted that this boiling away is not limited to tiny lava worlds. In the hunt for alien life, we have found many close and Neptune-sized planets whose fluffy hydrogen, helium envelopes are being stripped by high-energy photons from their stars. This process, called photoevaporation, peels off the light gases first, leaving behind a compact rocky or icy core. Kepler and test data show a suspicious lack of planets of certain sizes very close to their stars, as if many have already been carved down to bare super-Earths. But while we might label this as planetary death, there is a twist. Early in its history, Earth itself probably had a global magma ocean, with rock vapor in the upper atmosphere glowing above a molten surface. From far away, that would have looked very much like some of these doomed lava planets. So it's time to find out the truth. Sometimes, what looks like the end of a planet's story could resemble the beginning of a habitable one somewhere else. Optimistically speaking, these disintegrating worlds are giving us a preview of multiple fates. Some planets will be pared down to naked cores that might, briefly, pass through a Goldilocks zone. Others will be completely consumed, leaving only thin rings or dusty disks around their stars. And as we push to even more extreme environments, we will see that boiling a planet is only one item on the universe's long menu of ways to erase a world. Runaway greenhouse versus snowball Earth climate death traps. If boiling a planet is only one item on the menu, what happens when the atmosphere itself becomes the chef? Because sometimes, the very blanket that keeps a world warm and habitable turns into a trap that it can never escape. So, let's begin with one of the most terrifying climate tricks in the universe, the runaway greenhouse. Under normal conditions, a planet's atmosphere balances incoming starlight with outgoing heat. But if the surface warms enough, more water evaporates into the air. Water vapor is a powerful greenhouse gas, so this extra vapor traps more heat, which causes more evaporation, which traps even more heat. This means you get a feedback loop that accelerates on its own. Push that loop far enough, and the oceans do not just get warmer, they boil. The atmosphere fills with steam, the upper layers are blasted by the star's radiation, and hydrogen escapes to space. Over time, a once blue, Earth-like world can be stripped of its water entirely, leaving a dry, sterilized surface baked under a thick, suffocating sky. We do not have to imagine this from scratch. We have a nearby example. Venus is almost the same size and mass as Earth, in the same planetary system, formed from the same basic ingredients. Yet its surface is hot enough to melt lead, with pressures more than 90 times higher than Earth's, under a dense atmosphere of carbon dioxide with clouds of sulfuric acid. It should be noted that many planetary scientists think Venus once had significant water, perhaps even shallow oceans, before a runaway greenhouse turned it into the ultimate warning sign. But while runaway greenhouse is one climate death trap, there is an opposite extreme, runaway glaciation. If a planet cools and ice spreads from the poles toward lower latitudes, that bright ice reflects more of the star's light back into space. Less energy is absorbed, so the planet cools further, which grows more ice, which reflects even more light. Once again a feedback loop, but this time driving the world toward a global deep freeze. In the hunt for alien life, this is not just theory. Geological data on Earth show that our own planet may have entered snowball Earth states more than once, with ice reaching almost to the equator. Life survived, but only barely, probably huddled around volcanoes and thin cracks of open water. Optimistically speaking, that tells us that even extreme climates do not always erase a biosphere, but the balance between a living climate and a frozen or boiled one is razor thin. So it's time to find out the truth. These fates are not set only by the star's brightness. They are tied to what is happening inside the planet itself, and that internal engine can decide whether a world escapes or is locked forever into one of these climate death spirals. Dying from the inside. When a planet's heart goes cold, if a planet could look in a mirror, what would it fear more? A violent impact from outside, or the slow failure of its own heart? Because planets do not begin as cold, quiet rocks. They start out blazing. In the chaos of formation, young worlds are assembled by impacts that melt vast regions of their interiors. Add in the heat from radioactive elements decaying over time, and you get a deep, churning interior, molten cores, rising and sinking plumes of rock, and an engine that can run for billions of years. This internal engine does several critical jobs at once. Fast convection in a liquid, metallic core can act like a dynamo, generating a global magnetic field. Moving plates at the surface recycle crust, drag water and carbon into the mantle, and build continents and volcanoes. This means that, from the start, a planet's ability to host a stable atmosphere and a habitable climate is wired directly to how hot and restless it is inside. But while massive planets can hold on to that heat for a long time, smaller worlds leak it away. Over billions of years, they cool. The core begins to crystallize from the center outward. Convection slows, then weakens, then in some cases almost stops. The magnetic field flickers and fades. The surface freezes into a single rigid shell. Geology does not vanish overnight, but the pace drops from a roar to a whisper. Mars is our clearest warning. In the hunt for alien life, we often look at the red planet and imagine oceans that may once have covered its lowlands. Today, though, it is a cold desert with a paper-thin atmosphere. The leading picture is that Mars cooled quickly, its smaller core losing heat faster than Earth's. It should be noted that when its internal dynamo died, its global magnetic shield went with it. Without that shield, the solar wind had almost direct access to the Martian atmosphere. Over time, charged particles stripped gas away, atom by atom, helped by the planet's lower gravity. We have data from orbiters actually watching this escape in progress. Optimistically speaking, some pockets of subsurface water and perhaps even microbial life could still persist, but the surface environment has been transformed by this slow internal death. There is another consequence of a fading interior tectonic shutdown. On Earth, plate tectonics acts like a thermostat, cycling carbon between the atmosphere, oceans, and mantle. Volcanoes add greenhouse gases, weathering and subduction remove them. So, let's begin to see the danger. If the plates lock up, that long-term carbon cycle can fail. A planet without active tectonics may struggle to keep its climate in the narrow Goldilocks zone for complex life. Too much greenhouse gas, and you risk a Venus-style runaway. Too little, and you slide toward a frozen Mars. So it's time to find out the truth about our own world. Will Earth's core and tectonic engine eventually wind down as well? And if they do, what happens to our atmosphere? Our oceans, and everything that depends on them? Mars, a case study in internal planetary death. If we want to know how a planet like ours might die from the inside out, we do not have to look light years away. We already have a corpse in our own backyard. Mars is what happens when a world's interior gives up before its surface is ready to stop. All the evidence says early Mars was shockingly more Earth-like than the frozen desert we see today. Ancient river valleys snake across its crust. We see deltas where water slowed down and dropped sediment, and layered rocks that only really make sense if liquid water once persisted for millions of years. This means Mars must have had a thicker atmosphere to keep that water from instantly boiling or freezing away. We also see minerals that usually form in neutral to mildly salty water, not just in harsh acid. Optimistically speaking, those are exactly the kind of conditions we associate with a potentially habitable environment. In the hunt for alien life, a small, cool planet with long-lived lakes would have been a very tempting target. So what went wrong? It should be noted that Mars did not just lose its water, it lost its shield. When NASA orbiters mapped the magnetism locked into ancient Martian rocks, they found stripes and patches that only make sense if Mars once had a global magnetic field, just like Earth's. But that field is gone now. Sometime more than 4 billion years ago, the Martian dynamo switched off. Without a magnetic cocoon, the solar wind from our star could slam directly into the upper atmosphere. And with MAVEN, the Mars Atmosphere and Volatile Evolution mission, we have watched that process in real time. MAVEN has seen ions streaming away down the planet's magnetic tail, literally being stripped off by charged particles from the sun. During solar storms, the escape rate jumps, the atmosphere is peeled like an onion, one charged layer at a time. Why did Mars die first, while Earth is still very much alive inside? Size: Mars is only about half Earth's diameter, and roughly 1/10 the mass. That smaller mass means less internal heat to start with, and more surface area per unit volume to radiate it away. Its core cooled faster, convection slowed, and the dynamo that powered the magnetic field shut down early. Internal planetary death, we now see, depends strongly on how big the planet is. But while Mars shows us the danger of being too small, what about a world that is larger than Earth? Here is the pattern interrupt. A super-Earth 2 or 3 times our mass could keep its interior churning and its magnetic field running for far longer than either Earth or Mars. Yet that same strong gravity might hold on to a crushing atmosphere or lock in a global ocean hundreds of kilometers deep, burying continents and recycling. Bigger is not automatically safer. It is just a different path through the universe's menu of planetary fates. So, let's begin to ask a sharper question, not just whether a planet lives, but how long its interior can stay awake. Collisions, shredding, and tidal spaghettification. Planets' interior can fall asleep quietly. But what if the universe chooses violence instead? Planetary systems do not start as peaceful clockwork. They begin as crowded disks of gas, dust, and newborn worlds, all jostling for space. In the hunt for alien life, we often picture a serene Goldilocks zone, but early on, it is more like a demolition derby. Orbits cross, resonances build, and gravity turns close calls into head-on collisions that can strip atmospheres, melt crusts, or erase a planet entirely. This means that even a finished system is never truly finished. Over hundreds of millions of years, slow gravitational nudges from giant planets, passing stars, or hidden companions can destabilize orbits. A world that was once perfectly placed can be kicked inward, outward, or straight into another planet. One catastrophic impact can reset the clock on habitability or end it for good. Our own Earth carries the scar of such a near-death experience. The leading hypothesis for the Moon's formation is a colossal collision between the young Earth and a Mars-sized body we call Theia. Imagine two almost Earth-like planets colliding at several kilometers per second. Rock vaporizes, oceans and atmosphere are blasted into space, and a halo of molten debris briefly orbits the wreckage. From that incandescent ring, the Moon condenses. Earth is nearly destroyed, yet a new world is born in the aftermath. But while giant impacts can rebuild planets, tidal forces can shred them beyond repair. When a planet ventures inside the Roche limit of a massive body, a star, a white dwarf, even a black hole, the difference in gravity between its near and far sides becomes extreme. The planet is stretched, cracked, and finally torn apart into streams of rubble. Instead of a single solid world, you get a ring or disk of fragments slowly spiraling around the killer. We do not have to imagine this only in theory. Telescopes have found white dwarfs whose light is polluted with heavy elements like iron, silicon, and magnesium. It should be noted that these elements should have sunk deep inside the white dwarf long ago, leaving only pure hydrogen or helium at the surface. The only way to keep replenishing them is to feed the star a steady diet of rocky debris, shredded planets and asteroids raining down. Around some white dwarfs, we also see dusty disks glowing in infrared data, flat rings of ground-up rock where a planet once orbited. Optimistically speaking, this is planetary archaeology at its most dramatic. We are literally watching the remains of destroyed worlds. So it's time to find out the truth about the harshest endings, because the ultimate planetary deaths do not even require stars at all. Some worlds die slowly, as the entire universe itself runs out of usable energy, and that fate is far harder to escape. Rogue iceballs and subsurface embers, but what if a planet's star dies for that planet, without the star actually going anywhere? From the outside, the world looks finished. Inside, it may be anything but. When orbits are disturbed, some planets are not shredded or swallowed. They are simply flung away. A once orderly system can spit out a world at escape velocity, turning it into a rogue planet. No sunrise, no seasons, just endless night between the stars. It should be noted that this is not rare. Our data suggest there may be more of these dark wanderers than there are stars in the visible universe. So, let's begin with their power source. If you rip a planet away from its star, you do not instantly steal its heat. Deep inside, it still glows with residual formation heat, the energy left over from billions of years of being squeezed and stirred as it formed. On top of that, unstable elements in the interior keep decaying, releasing radioactive heat, and if that rogue world has a large moon, tidal forces can knead both bodies, generating frictional warmth the way Jupiter heats Io. On the surface, though, things are brutal. With no nearby star, the equilibrium temperature of a bare rock would plunge to just a few degrees above absolute zero. Any exposed atmosphere would condense or freeze out. But while the surface dies, the interior does not have to. This means the real question is, can anything trap that internal heat long enough for it to matter? Thick blankets of gas or ice can. A massive hydrogen atmosphere acts like an extreme winter coat, letting a rogue world keep a warm, high-pressure ocean under permanent night. Alternatively, a deep shell of ice, tens or hundreds of kilometers thick, can insulate a subsurface ocean from the vacuum outside. In the hunt for alien life, these frozen drifting pressure cookers suddenly look very interesting. We already have prototypes in our own system. Europa and Enceladus orbit far outside the Sun's classic Goldilocks zone, yet both hide liquid water beneath ice, sustained by tidal heating and internal radioactivity. Their surfaces are cryogenic deserts, but their interiors are geologically active, venting plumes that may carry organic chemistry. Swap the Sun for the galaxy itself, turn down the external light to almost nothing, and a similar story could unfold on a rogue iceball. Optimistically speaking, that makes these objects only half dead. From interstellar space, a rogue planet would be nearly invisible, a black marble radiating faint infrared heat. Land on the surface, and you might find a silent glacier stretching to a starless horizon. But drill down, and there could be liquid water, hydrothermal vents, maybe even ecosystems that have never seen starlight. So it's time to find out the truth about what death really means for a world, because even this lingering inner warmth is temporary. What happens when the radioactive embers go out? The last tidal flexing stops, and the entire universe itself slides toward a final, featureless chill. Planets in a dying universe, so if even radioactive embers fade, what happens next? When the last internal heat leaks away, a planet's fate is no longer decided by its own heart, but by the slow, vast machinery of the cosmos. Most stars, including our Sun, do not end in spectacular supernovae. They swell, shed their outer layers, and leave behind white dwarfs, Earth-sized stellar corpses with half a sun's mass. At first, these remnants are dazzlingly hot, and any surviving planets orbiting them are bathed in a harsh, blue-white glow. But while that light looks fierce, it is only the afterglow of fusion. Over trillions of years, the white dwarf cools, its spectrum reddens, and eventually it becomes a cold, black dwarf ember. Any loyal planets remain in orbit around a star that has effectively gone dark. It should be noted that this timescale is far longer than the current age of the universe. We have never seen a truly black dwarf because there has not been enough time for one to exist, yet the physics is clear. As the eons pass, more and more systems will look like this, a few dead planets circling a frozen cinder with no day, no night, and no real sky. But orbits are not eternal either. Over unimaginable spans, gravity keeps stirring the pot. Passing stars tug on planetary systems, reshaping orbits or flinging planets entirely into interstellar space. Close encounters with black holes can strip planets away or hurl them inward. Even when a system seems isolated, tiny effects like gravitational radiation slowly drain orbital energy, drawing planets ever closer to their stellar remnants. In the hunt for alien life, these details are usually background noise. Here, they become the main story, a long, slow cascade of scattering, capture, and decay, until most planets are either swallowed, shredded, or exiled as lonely rogues between the stars. And then, there is a deeper possibility. So, let's begin to stretch our timeline beyond even black dwarfs. If protons are unstable, as some theories predict, then matter itself has an expiration date. Over timescales of at least 10 years, the very particles that make up rock, ice, and iron would randomly decay. Mountains would not erode, they would evaporate at the level of their atoms. Optimistically speaking, this is the far edge of speculation, but if true, it means every planet is ultimately built from sand that cannot hold together forever. Layered on top of all this is the expansion of the universe. As galaxies accelerate away from each other, energy becomes more and more evenly spread out. This means temperature differences fade, and with them, the ability to do work. Heat death is not an explosion, it is the loss of contrast. No hot versus cold, no high versus low, no gradients to power geology, climate, or life. Planets, if any still exist, are not worlds in any meaningful sense. They are inert dust, drifting in a cosmos that has forgotten how to change. But let's interrupt this slide into eternity for a moment, because all of that is unimaginably far away. What does any of it actually imply for us, right now, on Earth? Our planet will not wait for proton decay or heat death. Its most likely death is scheduled much sooner, written into the life story of our own star. So it's time to find out the truth about how the sun will end Earth's habitability long before the universe itself goes dark. Earth's death menu, ranking our possible fates. So if Earth has a death sentence, which executioner should we actually be worried about? Out of the entire cosmic menu we have just explored, which options are really on the table for this one small blue planet? Let's start by clearing out the most dramatic, but least realistic, fates. Our sun will never explode as a supernova. It is simply not massive enough. That particular ending is reserved for much heavier stars, the giants of the galaxy. No supernova means no sun-forged shockwave tearing Earth apart in an instant. It should be noted that this also rules out a sun-driven gamma-ray burst. Those narrow, lethal beams come from collapsing massive stars or merging stellar corpses, not quiet, middle-aged suns like ours. Could a distant gamma-ray burst in our galaxy still hit us? In principle, yes, but while the universe is full of these events, the odds that one goes off close enough, pointed precisely at Earth during the tiny window when complex life exists here, seem extremely low. We also do not sit next to a hungry black hole, so total tidal shredding. The kind of destruction we see when a planet strays too close to a compact star is effectively off the list as well. What about orbital chaos? Could Earth be kicked out of the solar system, exiled as a rogue planet drifting through interstellar space? Long-term simulations of our system show that planetary orbits are technically chaotic over billions of years. Tiny changes grow, resonances shift, but while Mercury and Mars have some chance of dramatic rearrangements, the current best data suggest Earth's orbit stays relatively calm for the remaining main sequence lifetime of the Sun. No guaranteed ejection, no high-speed collision on the schedule. This means the leading external killers are slower and more intimate. As the sun brightens with age, Earth's climate will be pushed toward a runaway greenhouse. Oceans evaporate, water is lost to space, and the atmosphere thickens into something more Venus-like than Earth-like. Later, as the sun swells into a red giant, its outer layers may directly engulf our orbit, or at least blast the planet with so much energy that any remaining surface structure is incinerated. Optimistically speaking, that is hundreds of millions to billions of years away, but it is written into stellar evolution itself. Inside Earth, another clock is ticking. The core is cooling, the magnetic field will weaken, and plate tectonics may eventually slow or stop. Without a protective magnetic bubble and active geology recycling carbon, the atmosphere and climate could drift into an uninhabitable state long before the sun turns truly hostile. In the hunt for alien life, we often ask whether distant planets keep their dynamos and tectonics running. Here, those same questions decide our own expiration date. So, let's begin to ask the uncomfortable question. What actually gets us first? The suffocating atmosphere, the dying interior, or the evolving star? And how much of that timeline is still under our control? Reading the autopsy, how astronomers diagnose dead worlds, if planets can die in so many different ways, how do we actually know which fate they suffered? In a universe where we rarely see the crime in progress, how do we read the autopsy report of a dead world from light that has crossed dozens or hundreds of light years? So, let's begin with the basics. Transit photometry, radial velocity, and direct imaging look like dry technical terms, but together they act as our forensic toolkit. When a planet crosses in front of its star, the tiny dip in brightness reveals its size and orbit. Radial velocity, the subtle wobble of the star, gives us the planet's mass. This means, by combining both, we infer density and decide whether we're looking at a puffed-up gas world or a compact, Earth-like rock. In rare cases, direct imaging lets us see the glow of a planet itself, teasing out temperature and sometimes even crude atmospheric hints. But while those methods tell us what a planet is today, the real drama comes from what looks wrong. Some transit curves are not clean round-edged shadows. They are ragged, asymmetric, with long fading tails. That shape is a smoking gun for disintegration, a planet shedding dust or vapor like a comet. We have found ultra-short period worlds whose orbits are less than a day, their surfaces literally evaporating under intense starlight. Around other stars, infrared images reveal broad debris disks, rings of shattered rock and dust. These are the chalk outlines of past collisions and gravitational chaos. It should be noted that the most haunting evidence comes from white dwarfs, the cooling corpses of sun-like stars. Their atmospheres should be pure hydrogen or helium. yet many are polluted with iron, magnesium, and silicon. Those are planetary ingredients. The only way they get there is if asteroids, moons, or whole planets were tidally shredded and rained down onto the stellar remnant. We also see planets dying in real time through their spectral fingerprints. When a world is losing its atmosphere, escaping gases absorb starlight at very specific wavelengths. Long tails of hydrogen and helium have been detected trailing hot Neptunes and super-Earths, clear evidence of photoevaporation sculpting them into smaller, denser remnants. In some cases, we even see metal vapor, rock literally turned into gas. This is where the James Webb Space Telescope changes the game. JWST can dissect a planet's atmosphere during transit, measuring how much starlight is blocked at each wavelength. From that, we infer not just composition, but how thick the atmosphere is, how fast it is escaping, and what the thermal environment at the top of the sky must be. Optimistically speaking, we are no longer guessing at planetary life cycles, we are measuring them. JWST's infrared eyes also probe surface conditions on some worlds, telling us whether they are bare rock, wrapped in greenhouse blankets, or already sliding toward Venus like hellscapes. In the hunt for alien life, this forensic approach has an unsettling side effect. By cataloging dead and dying planets, we are quietly assembling a library of possible futures for Earth. So it's time to find out the truth. There is one more twist in these autopsies that changes how we think about our own planet's fate. Every planet dies. But not every planet is lost, so if planets can die in so many ways, is that really the end of their story? In the long view of the universe, death and birth are not opposites. They are steps in the same cycle. When a planet is shattered by a collision or stretched apart by a star's gravity, its fragments do not vanish. They spread out into glowing rings and dusty asteroid belts, raw material waiting in orbit. Over millions of years, that rubble can clump into new moons, new minor planets, even the seeds of an entirely new system of worlds. This means that every broken planet is, quietly, a construction site. We actually see hints of this. Around distant stars, including red dwarf systems, we detect warm belts of dust that look suspiciously like the aftermath of planetary demolition. Some white dwarf stars are polluted with heavy elements in their atmospheres, evidence that they have been feeding on shredded rocky worlds. It should be noted that those metals do not stay locked away forever. They enrich the star and any future protoplanetary disk with extra carbon, oxygen, iron, and more. In the hunt for alien life, those heavy elements matter. They help build complex minerals, thick atmospheres, and liquid water oceans. A planet that is engulfed or torn apart today can change the chemistry of planets that form billions of years from now. Even a catastrophic end can make the next generation of Earth-like worlds slightly more habitable. But while the rock is recycled, the story of a world is not erased so easily. Even so-called dead planets can carry fossils of their past in places we are only just learning to read. Crustal layers record ancient oceans and climates. Isotopies in the rocks remember how intense the star once was. Thin, leftover atmospheres can preserve odd mixtures of gases that only make sense if life once breathed there. Even the shape of an orbit can hint at past gravitational battles and lost companions. Optimistically speaking, that means Earth will leave a long, decipherable echo. Long after the biosphere fades, our continents will still show the scars of plate tectonics and long-vanished ice sheets. Our atmosphere will bear isotopic fingerprints of industrial chemistry and strange spikes of elements like plutonium, and scattered across the surface and in orbit will be artifacts, alloys that do not occur in nature, peculiar geometries, perhaps even dead satellites around a quiet planet. So, let's begin to reframe the question we started with. When we ask how planets die, what we are really asking is how long they can stay active, protective, and habitable, and what traces they leave behind when they finally fail. In other words, understanding planetary death is just another way of mapping the full fragile lifespan of worlds like our own. And that brings us to Earth's clock. Recap: the cosmic menu of planetary death. Earth's clock is not the only one ticking. When we zoom out, we see an entire menu of planetary endings playing out across the universe right now. So, let's begin our recap with the most obvious executioner, the star. Stellar-driven deaths come in several flavors. Slow brightening can quietly strip a planet's atmosphere and boil its oceans, as Venus likely did when the young sun turned up the heat. Red giant phases swell stars to hundreds of times their size, threatening to roast or engulf inner worlds. Polluted white dwarfs, packed with the ashes of shattered planets, are the grave markers of systems that passed through that fire. And on the violent end, supernovas and gamma-ray bursts can sterilize entire regions in seconds, blasting away atmospheres and chemistry in a single flash. But while stars can kill from the inside out, gravity can kill from the outside in. Orbital chaos reshapes a system over billions of years. We see planets spiraling inward on ultra-short orbits, like the disintegrating exoplanets with comet-like tails of rock vapor, doomed to be eaten by their star. Other worlds are thrown out instead, becoming rogue planets drifting through interstellar darkness. Some collide. The giant impact that likely formed Earth's moon is a reminder that catastrophic mergers are part of the normal life story of a planet. Then, there's the slow suffocation of atmospheric loss. Photoevaporation under intense starlight can strip away thick envelopes, turning mini-Neptunes into bare, rocky super-Earths. Stellar wind erosion and impacts can do the same over longer timescales, as Mars shows us with its thin, cold atmosphere and frozen deserts. In the hunt for alien life, this means we are often looking at survivors of a long atmospheric war, not pristine, untouched worlds. Inside each planet, another clock is running, as cores cool and magnetic fields fade. Surfaces lose their protection from charged particles. Tectonics can stall, volcanism quiets, and the recycling of carbon and water slows or stops. Mars, again, is our nearby example of internal shutdown. Its small size let it cool quickly, turning a once more Earth-like world into the quiet, rusted landscape we see today. Collisions and tidal shredding add the dramatic, rare events. We have watched entire planets being torn apart around white dwarfs, their debris feeding dusty rings. It should be noted that these extreme cases are just the visible tip of a much larger iceberg of orbital reshuffling and slow-motion demolition. And beyond all of this lie the exotic far future fates, rogue worlds freezing between the stars, planets skimming black holes and being stretched into streams, and finally, in a fading universe, everything cooling toward darkness. Optimistically speaking, that is the longest possible deadline. So where does Earth fit on this menu? Our most likely path is not a single dramatic event, but a sequence. Internal cooling will gradually weaken our magnetic field and tectonic engine. Atmospheric chemistry will shift as the sun brightens, pushing us out of the Goldilocks zone. Oceans retreat, weather patterns break down, and the surface slips from comfortably habitable to marginal, then to truly hostile for complex life. Long before the sun becomes a red giant, Earth may already be a world of microbial refuges, clinging to the last stable niches. Then, the stellar clock takes over completely. As the sun swells into its red giant phase, Earth will be roasted by increasing luminosity and tidal effects. Whether our planet is physically engulfed or just left as a scorched airless rock is still an open question, but either way, the habitable chapter will be long closed. This means the central insight of this entire journey is simple but profound. Planets do not have one death, they have many overlapping clocks. Orbital stability, internal heat, atmospheric protection, and stellar evolution each keep their own time, sometimes reinforcing one another, sometimes cutting each other short. Habitability is the brief interval where all those timers align in our favor. There's a kind of cosmic melancholy in that. Every example we have touched, Venus's runaway greenhouse, Mars's frozen silence, disintegrating exoplanets, rogue worlds, and the dusty remains around white dwarfs, shows a different way for that alignment to fail. Yet there is also grandeur, because it underlines how rare our present moment is. Right now, on this specific orbit, around this particular star, all of Earth's clocks are still overlapping in just the right way to support oceans, weather, chemistry, and conscious observers who can ask how planets live and die. So it's time to find out the truth that follows from that realization. If habitable windows are this fleeting, what should a civilization do with the one it has? Before our clock runs out, what you do with this knowledge. If every habitable window closes, what does that say about this one? All through this video, we have watched planets boil, freeze, fracture, and fall into their stars. None of those fates care about our politics, our arguments, or our schedules. But while our choices cannot stop the sun from brightening, they absolutely can decide how long Earth stays comfortable for us, and for the other species sharing this orbit. This means the distant deaths we have explored are not just cosmic horror stories, they are a timeline. A reminder that climate, atmosphere, oceans, and ice are fragile, temporary arrangements. A small tweak in greenhouse gases here, a shift in reflectivity there, and you either push a planet toward runaway greenhouse like Venus, or toward a deep freeze like a rogue world drifting between stars. So, let's begin treating planetary science as more than trivia about far-off systems. When we study how a red dwarf strips atmospheres from ultra-short period planets, or how a supernova shockwave can sterilize a Goldilocks zone, we are also learning how thin our own margin really is. It should be noted that the same physics that tears an exoplanet apart will one day reshape Earth's sky, oceans, and crust. In the hunt for alien life, We use worlds around other stars as laboratories, but they are also mirrors. A tidally locked planet losing its atmosphere to stellar wind, that is a warning. A frozen super-Earth with a dead core and no magnetic field, that is a preview. Optimistically speaking, if we understand these patterns early, we can stretch our habitable window far longer than it would last by accident. So, what can you actually do with that knowledge? Right now, on an ordinary day, on this very unordinary planet, you can keep following the data, watch more deep dives on exoplanets, on stellar evolution, on how atmospheres live and die, support space missions and observatories when you have the chance, because every spectrum we collect from a dying world out there helps us read subtle warning signs here. You can also defend curiosity itself, talk about these discoveries, share new results, treat long-term thinking as normal rather than strange. If enough of us grow up with a cosmic perspective, it becomes easier to make choices that protect climate, ecosystems, and the thin shell of air that makes Earth feel so effortlessly habitable. And now, one last question. Knowing that every planet has a death sentence, what would you most want future astronomers or distant civilizations to read in Earth's autopsy report? That we noticed the clock? That we used our brief stable era to understand the universe and to safeguard life, rather than to accelerate our own extinction? Tell us in the comments which planetary death fascinated you most, or which one quietly terrified you. Subscribe if you want to follow how this story unfolds, as new data rewrite the fates of worlds. And share this with someone who loves big cosmic questions, because the real twist is still ahead, the part where we decide what kind of ending Earth gets.